Oh boy. There I am. I'm being recorded. Oh boy. Well, there it is. So, like I already told them,
Yes.
we're conquering the universe in another way. And there we are blasting off. I'm going to go through this again, that the launch weight of JWST is so much less than the launch weight of Hubble Space Telescope. And I do want to spend some time talking about the telescope. And with a little luck, you'll be able to hear me on the computer, but I can't make any promises. Crank up your volume. So there's always the old question, why do we put telescopes in space? And the big selling point for the Hubble Space Telescope, you get up above the atmosphere and stuff. But since the Hubble Space Telescope went up, we have developed adaptive optics. And here's the Keck 10 meter looking at the galactic center without and with adaptive optics. So this is no longer a selling point. You can't convince people to let you put a telescope in space to do this because you can do it from the ground. But I mentioned this for two reasons. One is that it was a selling point for HST, and that has changed. The other reason is you probably think that adaptive optics is a DoD invention, and it's not. In fact, adaptive optics is an invention of, get ready for it, Mount Wilson Observatory. I keep telling everybody it's Mount Wilson, whatever it is, it's Mount Wilson Observatory. And the first adaptive optics system was actually conceived by Morris Babcock in 1951 or so. And he put one up in 1953 and one in 1947. But anyway, you can download my article and read it from the summer quarter 2021 reflections, which shows you how adaptive optics was invented at Mount Wilson Observatory. This is the reason that we put telescopes in space. Now, this plot shows you transmission. So 1 up at the top, where the line is, means perfectly transparent, you see everything. 0 down here at the bottom is you see nothing. And if you're going to look in the infrared, and remember the wavelength range, as you'll see, for JWST runs from about 0.6 to 28 microns. So this nicely covers the range of wavelengths seen by JWST. And there's a whole lot of you don't see anything, and a whole lot of you see maybe half or a third or whatever. You can't do reliable astronomy at these wavelengths from the ground. You have to get up above the atmosphere. That is a completely off-topic comment, and I'll only say it once. You want to know what causes global warming? It's right here. It's the 15 micron bending mode transition for CO2. Look it up. That's where it all comes from. So, first thing to notice about JWST is that it's big. Here it is posing for, it's not the real thing. This is a mock-up, of course, because if you put the real thing out there in the air, the grass and the dirt, they would just hang you. That would be the end of it. So here it is outside the Goddard Space Flight Center. As you might guess, just by looking at its size, shape, you can't stick that on a rocket, light the fuse, and send it into space. You've got to fold it up, and we'll talk about how it folds up. You know, in a few minutes here. So this is what you're looking at. This is a heat shield. I'm going to say something about the heat shield because it's kind of interesting. The pink color on the bottom is real. This is not an artistic concept. It's actually pink on the bottom. Computers and electronics are on the sun side. The telescope, it looks like it's probably a Ritchie-Chrétien or Cassegrain, but it's not. It is a premier anastigmat, and for you optics wonks, it's a coarse optical system. I actually have a slide later on I can show you if you want, buried in my extra slide. So the primary is ellipsoidal, the secondary is hyperbolic, and the science instruments are all on the back. So the first thing I want to say a little bit about is the heat shield, because this is kind of a unique affair. I've never seen one like this before. You can see it's big, and they say it's about the size of a tennis court. I give the dimensions up there, basically 29 by 14 meters. These layers are very thin. The thick layer, the one at the bottom, is 0.05 millimeters thick, and the rest of them are half that thickness. It's a Kapton film, so it's very thin. It's all 5 of these sheets are aluminized on both sides, and the bottom 2 have a silicon doping on the sun-facing side, which is where the pink color comes from. That's why it's pink on the bottom. So as you can tell, if you're 0.025 millimeters thick, you don't just wad this up and then throw it out in space and hope that it opens up just the way you want to, because it's not going to work. So it takes a little work, so we'll see how that happens. Meanwhile, this is how it works. You've got about 200 kilowatts hitting the bottom. Nothing's perfect. You would like to see everything reflect off, but it won't. Some of it will get through, and it will reflect off of the top layer and bounce as radiative energy, of course, bounce back and forth and leak out. But some of that will get through, and then some of that, and so on, up through 5 layers. The design specifications call for approximately 1 watt to get out the top, out of 200 kilowatts to hit the bottom. And the temperature targets, say, about 398 kelvins at the bottom to be 38 kelvins on the top. And so the question you ask, of course, is, did it work? Well, since JWST is actually sending back pictures and data and working, and everybody's all happy, it probably worked. You can guess that much. But I'll show you that it in fact did work. Here's what the temperature layout is like for the instruments. You can see on the bottom, the heat shield side is like 122 Fahrenheit. The instrument side is what's interesting. This is what you want to know over here. The 4 instruments, the near cam, near spec, the fine guidance sensors, and theory, they're all down around 38 kelvins. There's one, I think there's a 39. What happened? Why did my signal go away? Back. Oh boy, I didn't do anything. I was standing over here. I was far away from the computer. No idea what happened. And so it's just 36 or 39 Kelvin. Okay, it's 39 instead of 38. So we're 1 degree Kelvin in this case is not going to hurt us any. So we're doing fine. But the MIRI instrument, the long wavelength instrument, can't operate when it's that warm. It can only operate at a maximum of 7 kelvins. So it has an active cryo cooler on it. It's a closed loop system like a refrigerator. So it doesn't use up cryogen like the older telescopes. It can run forever, basically. And it's down to 6 Kelvin. So all the temperature, everything is working fine. The heat shield actually works. It met design specifications at a minimum and might have done a little bit better. But things don't always do that. So you should be happy that we've managed to accomplish that. Now, I did say that you can't just wad it up and send it. It's big. It's got to be folded up. So here it is being folded up at Northrop Grumman. You have to pack this thin sun shield material the way you would pack a parachute. You don't just jam your parachute into the pack, jump out of the airplane, and hope that when you pull the string, something will come out. That's not the way you do it. That's not the way you do it here. You spend $10 billion on something, and then it doesn't work. They come looking for you. You have to get out of town. So this is usually compared to origami, the way it's folded up. And I have a movie here, and I didn't mute my computer. I have no idea whether the cheesy NASA music will come on when I play it, but you can see the text at the top. I just want to tell you that this great big thing launched with 300 single point of failure items on it. That means there are 300 things, any one of which will kill the mission if it doesn't work. Just so you know how touchy things are. And the sun shield alone has 107 release mechanisms, 70 hinge assemblies, 400 pulleys, 90 cables totaling about 1,300 feet, and 8 deployment motors. All those things have to work for the sun shield to open up. So I'm going to play a movie and we'll see if the cheesy music plays or not. That will show you how it opens up. And the cheesy music is playing. So there you are. That all actually worked, which is kind of amazing. And the little thing called the momentum flap is to balance the solar torque. One of the problems with having something that big in sunlight shining on it is that the light pressure will torque the spacecraft. And you want to balance that. You want to minimize that because if you torque it, you've got to use up your fuel to pull your telescope back into the right orientation. And so the momentum flap is designed to do that. And it worked very well. So this, you can't put JWST into orbit around the Earth because the Earth is a searchlight, incredibly bright at the wavelengths, long wavelengths you want to observe. So you don't set your telescope up deliberately under a street light. You might have to, depending on what neighborhood you live in, but most of us try to at least get the house between the light and the telescope or something, right? And so that's what we're doing. We're going all the way out to Lagrange point. Up on the top, you see the layout of Lagrange points. These are balance points. You have to remember that this whole thing is rotating. This pattern is rigidly fixed to the Earth. As the Earth goes around the sun, this pattern goes around the sun with it. So you're not just balancing the force of gravity, you're balancing gravity and momentum. And so the L4 and 5 points are stable equilibria. That's where the Trojan asteroids hang out for all the planets. There's a bunch of junk and garbage there for the Earth too. The L1, 2, and 3 are unstable. If you put something there, it won't stay, it'll fly away. You've got to hold it there. The L1 point is where you put the solar telescopes. L2 is where we put the infrared telescopes. Planck went out there, Herschel, anything you want to look at long wavelength infrared to get away from the Earth. L3 on the other side of the sun is a favorite place for science fiction writers to hide counter Earth so we can't see it, right? And then the counter Earth people come and there's all kinds of weird stories. You can't put anything there and expect it to stay. So if you put counter Earth there, it will not stay there. It will come out from behind the sun. You'll see it. And so it doesn't work unless you've got a rocket engine that can hold the Earth in place. which is pretty good technology if you can come up with it. So we're going out to Lagrange point, and this telescope is going to orbit around it. And as you can see from the orbit characteristics up on top, the orbit of JWST around the L2 point is bigger than the orbit of the moon around the Earth. So one of the things people ask me many times, well, isn't it in the shadow of the Earth if you put it out at the L2 point? For a number of reasons, no, it isn't. And probably the best reason is because it's such a big orbit around the L2 point. It's way out in the sun, which is what you would expect because it's solar powered, and you don't put solar powered spacecraft in the shadow. Right? You put it where the sun shines on it. And so here is what the orbit looks like. So it's constantly pointing its sun shield and communications antenna towards the Earth. If you were out there at the L2 point looking back towards the sun, that dot in the middle is way too big to represent the size of the Earth. It's much smaller than that. It's about 1/60th of the diameter of the sun. So even if you were at the L2 point, there would be no shadow because it's way too small. Now, you may have heard this mirror was impacted by a meteorite during the getting open and getting ready to go. So here in the C3 section, it was a larger impact sooner than was expected, but everybody knows that anything you put out at the L2 point is going to get hit by micrometeorites. This is standard stuff. It's designed into everything you put out there. It was designed into the JWST. And for those of you who care about the appropriate optics, you can see that it made only a small change to the RMS wavefront error for the system, not enough to worry about. Most of the problem they can solve by slightly adjusting the angle and pinching the mirror segments. These hexagonal segments have little pinchers on the back. They can move up and down, they can tilt, they can stretch, they can do a bunch of stuff to these to counteract the effect of impacts and changes to the wavefront error of the optical system. Now, I do want to make a comparison between JWST and HST, the Hubble Space Telescope. And the first thing is size. As I already mentioned, as big as it is, its launch weight was only 55% of the Hubble Space Telescope's launch weight. So a lot of good engineering has gone into figuring out how to make these things bigger but lighter. I tried to scale this image by eyeball as best I could so that this length of the Hubble Space Telescope compares properly in scale to the length of JWST. I might have gotten a little bit off, but this is pretty close. So that's how much bigger it is than JWST, than the HST is. And of course, the collecting area, light collecting area for the mirrors, it's about 5 times bigger for JWST, which I don't think it's good enough for a whole magnitude, but almost 1 magnitude dimmer than HST. So in physical size, JWST is much bigger. Here's the wavelength comparison. Now, I worked, as many of you know, on the Spitzer Space Telescope. And I always think of JWST not as a follow-up for HST, but Spitzer, because Spitzer was an infrared mission that did not look any shorter than 3.6 microns. JWST bridges the gap between Spitzer and HST. Its shortest wavelength is 0.6 microns, which is just on the blue side of hydrogen alpha at 0.65 microns. Because really, if you're going to launch a telescope into space and you kill off your wavelengths just before you get to hydrogen alpha, that's another reason for hanging you from the building, right? You got to have hydrogen alpha because it's like the most common wavelength. And it goes out continuously, spectroscopy and imaging out to 28.3 microns. Spitzer had very limited long wavelength capabilities on the long wavelength instrument at 24/760 microns, fairly broadband, and the IRAC instrument from 3.6 to 8. But Spitzer had a very small mirror, less than a meter, 0.83 meters. So clearly JWST should be able to outperform it with such a large mirror, and does. I'll show you. I actually won't show you an example, but I'll get close to showing you an example. So you can see the James Webb Space Telescope is working in an area of wavelength that we've explored before, but only in bits and pieces. Spitzer only could see certain sections of that wavelength range. JWST sees it all, and it extends beyond most of what HST did. So this comparison image is one that comes from the JWST website. This is all eyeball visible light, optical light image of the famous pillars of creation from the Hubble Space Telescope. It's an image you've seen before. This was not the original 1995. This is the 2015 version, a little bit spiffier. So you can see you're looking at a lot of background, a lot of the environment around the dust clouds. So there's a sheet of hydrogen, ionized oxygen between us and the background stars. So you don't see much background here because you're looking at wavelengths that are sensitive to the gas around the dust clouds. So you can see the environment that the dust clouds live in. And the dust clouds are opaque. They're a wall that you can't see through. So most of what you see on this side is stuff between us and the dust cloud. You don't see through the dust clouds at these wavelengths. So they're dark, they're opaque. If you go over here, now the opposite. The dust clouds are shining at you. You're getting emission from molecular hydrogen, and you're getting thermal emission from the dust cloud. So instead of being dark, they're bright. They're a source of radiation, not a blocking of radiation. You're looking at Paschen alpha, so the Paschen line instead of the Balmer line of the hydrogen spectrum, and that's what's responsible for a lot of this blue glow in the background. So you see a lot more background stars, but you're still seeing the environment around the nebula. And so this is sold as by the JWST people as how you compare what HST does to what JWST does, but it's not a fair and proper comparison because while HST orbited the Earth and still does orbit the Earth, we had the capability at one time to go up there and swap instruments, change it. So its capabilities change with time. So in fact, HST had significant near-infrared capabilities. And so I pull this image. It's not scaled the same way because I'm too lazy to do that. But here's that same JWST image, only now here's HST at 1.1 and 1.6 microns. You're picking wavelengths that ignore all that stuff, the blue glow, the Paschen alpha, the oxygen, the hydrogen alpha. Now you can see in the Hubble image a lot more background stars. It all depends on the wavelengths that you look at. And at these wavelengths, the dust is not shining at you, but it's not opaque either. You can look through the dust and see a bunch of stuff on the other side, especially up in this pillar here. You see a lot more background objects than you saw before. So these three images, the optical Hubble, the infrared Hubble, and this JWST image, teach you a lesson, and I'll show you another example of it later on, that it really depends on the wavelength you choose what you see. So you have to decide in advance, I'm looking for that. Now you pick the wavelength that will show you that. If you're looking for the stuff around the clouds, you pick that wavelength, then you don't see the background objects because that's what you want to look at. If you want to look at the background object, then you don't use those wavelengths because you can't see them. Pick wavelengths that will allow you to see the things that you want to see. And that's especially the case if you want to probe these dust clouds to see what's inside them. This is the kind of wavelength you use, and you probably diddle it in more fine detail than I'm doing here, because you want to see an embedded star or something. You pick the wavelength to show you what it is you want to see. So I do want to introduce some of the science concepts before we get to what did JWST actually see. And of course, most of you know me well enough by now to know that Mount Wilson Observatory is never very far from any talk that I give. And the foundational concept of cosmology is the redshift distance relationship. That's why you need to push JWST out to longer wavelengths, like 28 microns, so you can see the high redshift galaxies, which are far away. So that all begins in 1929. Edwin Hubble, using a 100-inch telescope at Mount Wilson, published his results where he figured out the distances, the distant galaxies, using his Cepheid class variable stars and the discovery of Henrietta Swan Leavitt at Harvard College, that in fact you can do that. So he makes this plot. The redshift is on the vertical axis, expressed as a Doppler velocity, or relative velocity. And the distance is on the horizontal out to about a couple of million parsecs. Hubble figured out the distances himself. The velocity redshifts he's using come from Vesto Slipher at Lowell Observatory. But Hubble forgot to mention this in the paper. You're not supposed to do that then or now. And it gets you into trouble if you take somebody else's data and publish it and pretend it's yours. So it got him into some trouble too. But after he published this, then he went to work with Milton Humason, the guy who famously started out as a janitor at Mount Wilson Observatory because he wanted to hang around the chief electrician's daughter. It worked. He married her and he got the job and became a famous astronomer in his own right. And then the plot over on the right, a couple of years later. Now, the little chunk of points down here in this corner, that little chunk of points is this entire plot over here. And so it's a pretty linear relationship. And that this is where it all begins. Been modified significantly since then. Modern cosmology doesn't look exactly like that, but that's where it starts. So the whole thing that we're working on now, the distant galaxy expansion of the universe, all that comes from research that first began at Mount Wilson. So what are the objectives? Why are we sending JWST for $10 billion up into space? Well, one thing is we want to see the formation of the first stars and galaxies as it happens. And everybody keeps saying their telescope is going to see it, and then it doesn't. And so I'll believe it when it happens. Hasn't so far, but you never know. JWST should be capable of doing it. We want to see how galaxies evolve through the history of the universe, stellar evolution, the life cycles of stars that is easy to probe when you have good spectroscopy like you get from JWST, and extrasolar planets. And I point out that this diagram was made in the pre-launch publication, and therefore some of these numbers, especially those numbers right there, from 200 to 400 million years for the first stars to form, may be and probably already are being stressed by data coming out of the JWST. We may find stars are forming earlier than we thought. Here are just a list of the instruments and detectors. There's a near-infrared camera, a near-infrared spectrograph. The wavelength ranges for the instruments are given here. The near-infrared imager and slitless spectrograph and the mid-infrared instrument, the MIRI, that's the one that needs to be at 6 kelvins in order to work right. The others you can get by 38 kelvins, but it has imaging capability, of course, coronagraphic imaging, that's for looking at extrasolar planets. The coronagraph is a little physical disk that sticks into the optical path physically and blocks out the star so you can see a planet. The spectroscopy in time series, which means you can watch things get dimmer and brighter, and so on. The wavelengths, you are sensitive to starlight and gas and hot dust. At the longer wavelengths, still you see gas, but warmer dust, exoplanets, particularly at the longer wavelengths, and of course high redshift galaxies, which is one of the big things that they're really looking for. But there is another technology I want to talk a little bit about that is connected to the near infrared spectrograph. This is really special. This is the first example I'm aware of where nanotechnology meets astronomy. So you probably know, many of you, that one of the techniques used for ground-based astronomy is to have your machine shop drill holes in the mast that you put on the front end of the telescope, and then you connect each hole with fiber optics to an integral field spectrometer or something like that. And that way you only see the light from the targets that you want to see. On the ground, it's pretty easy to do. You call somebody up with the machine shop, drill holes here, and they go drill, and they send you a thing and you set it up and it works. You can't do that at the Lagrange point. You have a problem. So what they've done is put a mask that you can put in front of the near-infrared spectrograph with 248,000 micro shutters, which are 100 by 200 microns in measurement. And those of you who can afford to do it, if you pluck a hair out of your head and look at the end of it, that's about 100 microns across. So you pluck two, which could be pretty savage, but then that's it. That's those two little hairs. That's what you're looking at. They're electromagnetically controlled. There's not a mechanical thing. They run a couple of charge passes and a magnetic thing, and I don't remember the exact detail. It takes a little bit of work, but they can open and close each one of these by changing the charge state on that particular window. And then the light just falls on the detectors. No fiber optics like this goes through, falls on the detector. And as the little window up here tells you, that allows you to see the light from the object you want to see without extra light spilling into the optical system and bouncing around and confusing. And so this is the first time I've ever seen this kind of nanotechnology go to work on a big space telescope. I thought it was very spiffy. So now, a little bit about the observations. What are we looking at? Now remember, we want to see high redshift galaxies in the very early universe. There are two ways you can do that. The first way is here. This, from the Cosmic Evolution Early Release Science Survey, object number 93316, has a photometric redshift of 16.4, which is enormous. It's crazy. And so what you look for in your data, each one of these orange points is a photometric data point. So you're measuring the brightness of the object at each one of these points, and there are 1, 2, 3, 4, 5, 6, 7 points, right? So that's all you have is 7 points. You don't have a spectrum, you just have these 7 points. But there's a pattern that's typical of high redshift galaxies. You don't see it here, you don't see it here, maybe you'll see it here, maybe you won't, but suddenly you see it up here. And so the pattern is really low, up, and then down. And that tells you that you might have a galaxy. And from the photometry, you can get a redshift, and you do it by modeling the galaxy spectrums. That's what this green line is. It's a computed model. The software they use is something called bagpipes, and it creates a model galaxy spectrum, and then you shove it around until it fits your data points, and it comes out with a redshift of 16.4. If that is correct, if that stands up to further investigation, that means the light travel time distance to this galaxy is 13.4 billion light years, and the age of the universe with the galaxy sitting in it is 240 million years after the bang. And remember that 200 to 400 million years is when we expect the first stars to form and we have a galaxy. So this can stress the mind of someone whose job it is to figure out how to get galaxies to form so fast. But it is a photometric redshift. You can be fooled. It might not be correct. You can look at a brown dwarf and think you're looking at a galaxy. It's easy to do. You're just using photometry. You need a spectrum. In this case, not only is this redshift wrong, it is spectacularly wrong. So in an effort to spectroscopically confirm this redshift, everybody waiting, in fact, the spectrum shows that its redshift is only 4.9. That is a huge difference. It's actually 12.5 billion light years away, and the age of the universe is actually 1.213 billion, about 1.2 billion years. So nobody cares about a galaxy in the universe 1.2 billion years after the Big Bang. Lots of them, but 4.9. So you have most of the redshifts you see on any papers, any articles, anything that comes out of JWST, the vast majority of the redshifts you see will be photometric redshifts, and they might be fooling you. You can't assume it's correct. If you're going to make some profound statement like, I just found a galaxy in the universe 240 million years old, you better do a spectrum and make sure. And in this case, it turned out to be vastly wrong. This is what you want, a spectroscopic redshift. That's the real thing. The photometric redshift is not. And so the highest spectroscopically confirmed redshift that I'm aware of so far is 13.2, the galaxy up at the top, which is 13.395 billion light years away, or 33 billion light years away, and the age of the universe where the galaxy is sitting is 325 million years after the bang, inside that 200 to 400 million year range where you expect the first stars to form. I'm showing you two distances. The GLY is gigalight years, right, for a billion light years. This first distance, 13 billion light years, is the light travel time distance. Everybody always uses this as a distance. You ask somebody, how far away is that galaxy? They'll tell you it's 13.267 billion light years away, and it's not. It is a ridiculous number to use for a distance. Nobody should ever call that a distance, but they do it anyway, always. Problem is, this is actually a distance in time. It is not a distance in space, should never be used as a distance in space. It tells you how long it took the light to get from there to you, 13.2 billion years. But remember, during those 13.2 billion years, the universe is expanding. So when the light gets to us, if you pretend you're Dumbledore, like I sometimes do, and you wave your wand around and you stop the expansion of the universe, get out your yardstick, pace off the distance from here to there, you would pace off 31.7 billion light years worth of miles. So if you multiply either one of these by the speed of light, you're going to get a distance. This one is a fake distance. This one is the real distance. The way we think of distance, like how many rulers lay out between us and them, this is the correct distance. This is not. In every source you'll ever see, this is the distance you're going to get, the light travel time distance. So just remember that it's actually a measure of time. It's not a measure of distance. Say that to most amateur astronomers or anybody else. When they say, oh, no, you're wrong, it's a distance, and just tell them they're full of whatever and send it to me and I'll fix it. And so here we're seeing the universe inside 400 billion years mostly. So we're looking back. But there's no indication in any of these of population 3 or the primordial first stars that are all hydrogen. We haven't seen any of that yet. But we're pushing it. We're 346 million years after the bang. We're getting close. Haven't got there yet. But for those same 4 galaxies, kind of interesting. There's a whole bunch of stuff. The photometric redshift and the spectroscopic redshift, these 2 numbers up here, are actually pretty close together for these 4 galaxies. Most of the time they are, but not always. So depending on how important your conclusions are to you, you must worry about spectroscopic confirmation. The magnitudes, right a second, it's minus 27 declination. You might be able to see it from here or go a little bit further south and look for them if you want to, but the apparent magnitudes are all basically 28th, 29th magnitude objects. Most of you are probably not going to be able to see a 28th magnitude object in your telescope, but you're welcome to try. Up here in the red box is the base 10 logarithm of the stellar mass of these galaxies. Dark matter is not involved. We're seeing the light, and so we're going to see the light that eventually comes from stars. Why is hot gas hot? Because stars heat it up. Why is dust warm? Because stars heat it up. You're looking at stars and stuff heated by stars. All the light energy you get comes from stars one way or another. So you can derive the stellar mass, and that's what's given here. And you can see those numbers are on the order of 8, high 7s, low 8s. That number, the base 10 logarithm for the stellar mass of the Large Magellanic Cloud is 9.4. So these galaxies are all roughly a tenth as massive as the LMC. So they count as dwarf galaxies in the standard of our own local group of galaxies. They're particularly small. They're not terribly big. That's all right. I mean, they're fairly high redshift. We're not stunned yet at the high mass. They're small galaxies by our standard. But if you look at the star formation rate, which is the next to the last column, those star formation rates are all higher than the Milky Way, between 1 and 2 solar masses per year. Whereas in the Milky Way, it's about 1 or a little less than 1 solar mass per year. So these galaxies have a low mass, but they have a high star formation rate. So does that imply that in the early universe, we expect galaxies to be still forming and have a high star formation? I don't know, but that's what appears to be the case here. And the last column is the average age of the stars in the galaxy in millions of years. And they're all very small, 70 to 16. So they're fairly young. At least the stars that we can see are mostly young stars. So these galaxies are young, they're low mass. We're pushing towards that. Where do the galaxies start? We haven't got there yet, but we're working on that direction. Now this image down here is the JWST deep field that President Biden made a big deal about introducing in July a year ago. It took 12 and a half hours of exposure time, and it's 0.9 to 4.4 microns. So they call it a deep field. So let's compare it with the Hubble deep field up here. So there's the Hubble deep field. It took 155 hours to exposure time to get the Hubble deep field, and they very deliberately picked the emptiest piece of sky they could find. They searched hard. They didn't just look at it. They searched. They really looked. Where can I find a piece of the sky that's got nothing in it and nothing anywhere near it that could fool around with it? We'll look there and stare, and we get about 5,000 galaxies. JWST did exactly the opposite. They looked for a crowded piece of sky. They looked for a foreground galaxy cluster and looked at that, and that's what you see here. And both of these images are the angular size of a dime held at 75 feet. I forgot to bring a dime with me, but you know, the dimes, it's about that big, roughly speaking. And so you can see how big a piece of your whole sky, something that small would be. And there are 5,000 galaxies in there. So there's a lot of galaxies. Somebody asked how many galaxies are there in the universe, I say a lot. Because that's pretty about all. It's a lot. So let's zoom in on that image. There's a list of wavelengths for those of you who want to know. Now, I told you the difference between the light travel time distance and the real distance called the proper distance. Inside about 1 billion light years, they're pretty much the same. You don't need to worry about it. But in this case, the cluster, the foreground cluster, light travel time distance is 4.2 billion light years, but the co-moving distance, the proper distance is almost 5 billion light years. So the difference is significant. And it gets more significant the farther away you get, as you saw in the earlier galaxies where 13 became 30. So depending on what it is you're trying to do, you need to pay attention to what distance. There's actually several different ways to get a distance. All give you different numbers. You got to know which distance it is you're working with, but to understand. So why did JWST point here to make a deep field? Well, right away, you can see the foreground galaxy cluster is doing gravitational lensing. Like this is a gravitationally lensed galaxy image. So is that. All these little curvy things up there. And there are multiple images of the same galaxy in many instances. You've seen images like this before, and you know that a gravitational lens will stretch and distort a galaxy, but it will also magnify. This acts like a magnifying glass, and it can magnify a galaxy by a factor of 1,000 or 2,000 in brightness, which means that if you look at a galaxy cluster like this and then search for high redshift objects in the image, you will find objects here that you will not find if you look at an empty piece of sky like the Hubble Space Telescope did, because you don't have a magnifying glass in front of your telescope. Here you do. So you'll be able to detect high redshift galaxies preferentially by looking through a gravitational lens. And that's what they're doing here, looking for high redshift galaxies behind this image. And so here is a plot that shows you the photometric redshift. They're all photometric redshift plotted here against the base 10 logarithm of the stellar mass of the galaxy. Now remember, the foreground galaxy cluster has a redshift of about 0.4. And so all these galaxies here, this is the galaxy cluster in the foreground. And of course, behind it, there's a lot of galaxies. The farther away things are, the dimmer they appear to be, which is not surprising. So the farther away things get, meaning the higher their redshift, the fewer of them you should see, because you're only seeing the brightest ones. You're going to miss the dimmer ones, but they're too dim. The upper red line is represents the stellar mass of the Milky Way. And the lower red line is the stellar mass of the Large Magellanic Cloud. None of these dots are terribly surprising except object 399, which is marked up there. And it has a stellar mass based on its photometric redshift, which needs to be verified, of about 2.88 times 10 to the 10 solar masses. I should have written solar mass on the slide, but I didn't. Sorry about that. The Milky Way stellar mass is just over 6 times 10 to the 10, or 60 billion solar masses. Most of the mass of the Milky Way, like everything else, is dark matter. Stellar mass is only about 10%. But you can see this object is only about a third, actually more than a third, of the mass of the Milky Way, but it has a redshift of nearly 13, which puts it 785 million years after the bang. Redshift of 6.9, the light travel time distance is almost 13 billion light years. So this is beginning to be a problem. It's a very high mass galaxy for that redshift. We didn't expect to see a galaxy that massive until after at least 1 billion years after the Bang. This is significantly before 1 billion. And so that galaxy, more than any other, if this redshift holds out, is going to add stress to the lives of people whose job it is to figure out how to make a galaxy like that. If you search the wisdom of the internet, you will find a very large number of people telling you that dot proves that Big Bang cosmology is entirely wrong. No, it does prove that galaxies probably form faster and sooner than we expected, which is not terribly surprising because whenever you look up at the sky for something new, you always find something that doesn't fit the way you thought things would. If you kept just verifying what you thought you already knew, you would eventually just quit and go do something else because it's boring. I already knew that. And so, yes, this is going to be a problem, but it's a problem for galaxy formation, not for cosmology. Now let's go back to this image and concentrate here on an interesting object found in this image, which has been dubbed the sparkler galaxy. It's a redshift 1.3, nearly 1.4, spectroscopically confirmed, so it's a real redshift. Its light travel time distance is about 9 billion light years. It's over 13.5 for the real distance. So what is so interesting about the object in that circle? Well, these 3 images labeled 1, 2, and 3 are separate images of the same object, which is typical in gravitational lenses. You see multiple images of the same object all the time. This is the easiest one to look at. And here are the sparklers, these little dots. So they are point sources for JWST, not result, but they are probably globular clusters. The fact that they show up in all 3 images indicates that they are not likely to be an artifact of the data or an artifact of the telescope. Otherwise, they'd show up in one image and not in another. They all show up in this in all 3 images. Now, this object was observed by the Hubble Space Telescope, and here we're comparing the Hubble images in blue text with the JWST images of the red text. And you'll notice that in the HST images, you don't see the sparklers, the globular clusters, probably. In the JWST images, you do. Now, if you study the JWST images, you'll notice little dark spots, maybe, on the HST images and claim that HST actually detected these things. But if you did not have the JWST images to guide and train your eye, you would never look at the HST images and claim anything. And in fact, nobody ever did. This looks like noise. This is called confusion noise. And maybe if you ran an appropriate image enhancer or resolution enhancer, you might see them, probably not. So they're detected by JWST, and the difference is JWST has a 6.6 meter mirror, and HST has a 1.5 meter mirror, 2.5 meters. So here's another difference between JWST and HST, just caused by the mirror. Probably globular clusters, and they appear to be about 4 billion years old based on their photometry, which implies they formed about 500 million years after the Bang, which again is in keeping with the idea that the first stars formed somewhere in the first 200 to 400 million years. So far we haven't broken it, we just kind of stressed it. Another interesting thing, to me at least, is the high redshift identification of an individual star, which has been dubbed Arundel, not because of J.R.R. Tolkien's use of the word, but because it's an old English word that he borrowed that basically means something like star. I don't remember what it means. This red dash through the diagonally through the image is called the sunrise arc. This object was observed by the Hubble Space Telescope, discovered by the Hubble Space Telescope, but they couldn't tell what it was. They just had a bright spot. JWST was big enough to get a spectrum of it, or at least do photometry on it. And they decided that most likely it is a single hot class B or luminous blue variable star, but it could be a binary. It could be a cooler class B star along with another, not a luminous blue variable, but maybe a K class star, something, an O star, an O star. So it's going to be one of these, binary or a single star, but we don't know for sure which. But there we are looking at individual stars at high redshift, which is pretty good. Now, this object I include because it's an object I worked with on the Spitzer Space Telescope. This is a Spitzer image, and these are the JWST images, which is you have, because it has a bigger mirror, has much higher spatial resolution. This is a young stellar object. Star formation is one of the things that JWST is supposed to do. But primary reason I put it up here is to introduce you to the idea of astrochemistry. Astrophysics get a lot of press. Astrochemistry gets almost no press, but in fact, it's a really fascinating study because chemical reactions happen even at 100 kelvins or less than 100 kelvins. In the interstellar medium, there's a lot of chemistry going on, and you can see many of the molecules identified in this spectrum. There's methanol, water. There's a complex organic molecule region that's labeled up there, COM, is what's expanded here in the inner plot. And there's a whole bunch of, so I'm not a chemist, so I can't read off what all those things are other than the formula that's given there. But the idea is over here, you can see there's methane up there and ammonia down here, along with water bending mode. Look at this. This wavelength here is not the observed wavelength. This is a rest frame Earth laboratory wavelength. It's been translated. The redshift has been removed. Most of the chemistry that goes on in something like this is surface chemistry. It happens on a dust grain. It doesn't happen in the gas phase because you can't do it and conserve momentum at the same time. But on the surface of a dust grain, you can. And so there's a lot of surface chemistry going on, even down like 10 kelvins. There's chemistry going on, and the astrochemists deserve a shout out. And this is a moderate resolution spectrum from Miriam. Now, one of the other things, remember, was extrasolar planets. So here is a coronagraphic image of an extrasolar planet around this Hipparcos 65426. The star here represents where the star is, but it's blocked by something called the Leo stop, LYOT, that physically blocks the starlight so that you can see the light from the planet. Otherwise, you'd be lost in the glare. I show you this for two reasons. One is, yes, we can directly image extrasolar planets, not transiting, not the radial velocity. We just look at them and see them. There it is, right there. But this is an image that you see on the front face web page where they're trying to impress you with what the telescope does. These are not cameras like your cell phone that you click, and there it is. This is what they show you. But this is what comes out of the telescope right here. That little stalk that gets in the way of the star does not stop most of the light. It's most of the light it does. A lot of light it doesn't. So this mess is what actually comes out of the telescope. And then they give this mess to somebody like me, because this is what I did for the Spitzer Space Telescope. And they say, make it look good. Okay, I will make it look good. And the way you do that is you subtract the point spread function. It's actually called the point response function, but don't worry about the jargon. You subtract the point spread function of the telescope from the image, play around with it a little bit, and make it look good. And so that's what, there's a couple of different ways of doing that. I don't remember what ADI and RDI stand for, but there are ways of doing that. And so after you subtract out the light, then you get an image that looks like the image that's over there on the end, and that's what they put on the web page. Now, this is a process that you don't see. Nobody talks about it. You look at an image and they all have a great image. They just took this. All the images you see for anything like JWST are cleaned up like this by artists, made to look good. And so when you look at an image like this, just remember some poor soul took a mess and turned it into something that would look good on the web page. And it's real. And the hamburger shape is an artifact of the subtraction process. So another interesting thing, this is the Tarantula Nebula, which you may be familiar with in the Large Magellanic Cloud. This is probably the most massive and brightest star cluster in the Milky Way and satellite system, maybe in the whole local group. It's really quite amazing. This is where the R136 cluster is, that bright knot of stars in the middle. Just 8 of those stars total over 1,000 solar masses. The most massive stars in our part of the universe are in that cluster right there. Hugely massive stars that are close to 200 solar masses, which are probably binary, because I think if you get much over 100 solar masses, you're just going crazy. But supermassive stars. So what you're seeing is the star cluster and a lot of emission from the gas and dust around it that's heated up by the cluster. So one of the reasons for showing you an image like this is because it's a pretty picture, and you like to see those during talks like this, and so here is one. Another reason is you will see pictures all over the internet. James Webb Space Telescope just photographed God, whatever. It's all kinds of stuff. Look at that star. It has a very characteristic 8-point diffraction pattern. 6 symmetrical points and that horizontal red line. If you look at one of those funny images and you don't see that diffraction pattern, it's not the James Webb Space Telescope. The other reason for showing you this is a near cam image. So it's near infrared. Suppose we look at it at longer wavelength periods. Well, dang, the whole star cluster vanished. Remember that at short wavelengths, you're sensitive to starlight. At long wavelengths, you are not. And you may very well not see the stars because they're just not emitting enough long wavelength light to trigger your detector. But if you look at this spot here and this spot here, this is clearly hot and emitting something. And so you look at an image like this and say, that thing's hot, but there's nothing there to heat it up. I'll bet there's a star cluster there. Then you would look at it with this and say, aha, see, told you there was a star cluster. So you can tell, and of course the bright core of the cluster is visible there. And so this is another example like the Pillars of Creation image. The wavelength that you choose to make your observations will tell you what it can see. So if you know what you're looking for, if you know you're looking for a star cluster in advance, you would never use this instrument because you know in advance it won't see one. You use that instrument. So you pick the wavelength depending on what it is you're trying to see. And if you want to see a lot and just figure out what's going on, then you use every wavelength you've got, put them all together to okay, what's heating what kind of gas is this, what's chemistry, what's it made out of, all that good stuff. Now, amongst the science objectives for JWST, you did not see anything in the solar system. it's all out there. But that doesn't mean they didn't look at anything in the solar system. So there is a peculiar, relatively new class of objects called main belt comets, which are sort of half asteroid, half comet, weird things. And that's what comet 238P Reed is. 103P Hartley is one that you know, you probably looked at it yourself. And so the blue curve up on top is Hartley spectrum as observed by deep impact mission, which I don't think it impacted Hartley. It impacted another comet. It went by and made a spectrum. And so these are offset from each other so you can see what's going on. But the blue curve on the top for Hartley comes down, and then there's a water emission feature, and then it comes down and it goes back up at longer wavelengths. So it's brighter as you get redder, and there is emission feature from carbon dioxide ice on the surface. If you look at the comet Reed line, you see the water emission feature. Everything's fine until you get to about 3 microns, and it does not get brighter like the other one. It just continues to get dimmer. And there's no CO2 feature. Now, this object does act like a comet. It's got a halo and a coma, and it looks like a comet, but it has essentially no CO2, which is not right. Comets all have CO2. So why does this object not have CO2? Good question. Somebody will have to figure it out. And of course, the shape of the curve is much different, which implies that there's a lot less ice on the surface, and you're probably seeing mostly the bare rocks or the tholins that make things red instead of the high reflectivity. So this is a way to probe what is this thing that we're looking at. We don't know. Another interesting result is that there is a water torus around Saturn. So the water that comes out of Enceladus, which is the jet-powered satellite. So there's a water torus, and these are various spectra. There's a spectrum here for the plume, which has a lot of water in it. There's a spectrum for the whole area, a spectrum for the center. So this is the center. I think this is the torus section, and that's the plume. So what we see basically is that there is a new feature around Saturn, a ring of water that comes from Enceladus. And of course, everybody likes to see a nice color image of Jupiter. Remember that this is an infrared telescope, and all the images you're seeing are infrared, which means there's no such thing as true color. If you saw true color, we would just turn off the projector and turn off the lights, and that would be true color infrared. Because you make up whatever colors you want for the various wavelengths and bands. But here in the infrared, you're looking a little deeper. When you look at it with your eyes, you see the top of the clouds. Now you're seeing a little deeper into the clouds, but you're still seeing the outermost layers of the planet, the great red spot, and the characteristic bands and stuff that you're used to seeing. And here, the aurora at the southern pole is so bright that it makes a diffraction spike. And likewise, Io, which is off image over on the left, has its own diffraction spike. And we can see the rings of Jupiter, of course, in this image. And here is Neptune. Now, remember that Neptune and Uranus look very blue, even to your eyeballs in the Voyager images. The reason it looks blue is there is a great deal of methane in the atmospheres of both planets, and methane sucks up red light like a sponge. So while everything else looks bright and is shiny, when you look at Neptune with JWST, it looks dark. And the bright, shiny stuff are the ammonia clouds up above the main atmosphere of the planet. But the atmosphere of the planet itself is dark because you're looking towards the red, and the methane is sucking it up. So you're not seeing as much light because of the methane in the atmosphere. And of course, no matter what you do, point your telescope at anything these days, there will be some galaxy photographing. When I started doing this 50 years ago or something, crazy thing like that, we used 35mm slides, and you'd have an object in there. And if you had a background galaxy in your image, you'd jump up and down. See, I caught one. Can't avoid them now. They're just everywhere. So what does all this boil down to? This comes from the document reporting on this characteristics of the telescope. I'll just read it, although you might be able to read it yourself from where you are. Moreover, almost across the board, the science performance of JWST is better than expected. The optics are better aligned. The point spread function is sharper with higher encircled energy, and the optical performance is more time stable than requirements. The fine guidance system points the observatory several times more accurately and precisely than required. The mirrors are cleaner than requirements, which translates into lower than expected levels of near infrared stray light, meaning that the less than 5 micron sky background will be darker for JWST than expected. Now, you would think if you're in space, you wouldn't have to worry about background like we do the sky, but you do. It's not background sky, it's background light scattered by your optics. And so this means there's less scattered light and therefore better transparency, better seeing. The science instruments have generally higher total system throughput than pre-launch expectations. Detector noise properties are similar to ground tests, albeit with higher rates of cosmic rays as expected in deep space. Collectively, these factors translate into substantially better sensitivity for most instruments work than was assumed in the exposure time calculator for cycle 1 planning, in many cases by tens of percent. In most cases, JWST will go deeper faster than expected. And finally, JWST has enough propellant on board to last at least 20 years. That is extremely important because everything is delayed, but you know that now the next generation of extremely large telescopes is already under construction in the Chilean Andes. The European extremely large telescope with a 39-meter aperture, the giant Magellan telescope with an effective aperture of 24.5 meters are actually under construction. Okay, the 30-meter on Hawaii has been delayed, and they have problems. Who knows when they will be able to build it. But at least 2 of them are under construction. Give them a few years, and they will be in a position to do follow-up observations using adaptive optics to things discovered by JWST. Now, obviously, if you remember from the earlier plot, there are a lot of wavelengths that don't penetrate the Earth's atmosphere that you will not be able to follow up on from the ground, but there's a lot of stuff that you will. And so JWST will see something, and 6.5 meters sounds pretty good, but 30 meters is even better. And so if you find something, you say, hey, 30-meter guys, look at this. And okay, it looks like this. And so I really like that. And of course, it needs the propellant because remember that the L2 point is an unstable equilibrium path to keep it under power. You put it in an orbit, it will stay in a, and then it will kind of, go away. So you got to push it, do little orbital corrections. And you also need to use reaction fuel to maintain the orientation of the spacecraft. It's a typical spacecraft problem. You have reaction wheels on board that handle the angular momentum for you until they're spinning as fast as they can. And then they can't do anything more. You have to slow them down. You have to fire some jets and take the momentum off the momentum wheels in order to start the system up again. So 20 years is really good. And with that, I'm done. Thank you. So I guess I'll take questions.
Yeah, we got 20 minutes.
Yeah.
While we're doing that, do you guys mind if I get a picture of the group? That's just so great to get back together. I want to commemorate the event, get something for the newsletter.
Why don't you let me take the picture and you can sit in there.
Nobody needs to see me.
Now let's push that. Okay, now. In order to get you all. Okay, that looks pretty good. I think I'm getting just about everybody. I might miss you. I did move over.
Thought of making your own hardware seems too daunting.
Oh, boy, that looks like everybody. Okay,
Outstanding.
Thank you.
yeah. So somebody must have a question.
Why is that? What's stopping you? Why not breathe?
Well, I heard that the launch was so precise and better than expected that it gave
What if I told you?
more fuel to the telescope operations, right?
No, I didn't hear all that.
Okay, I heard that the launch was so precise that JWS didn't
Yeah.
need as much fuel to get to where it's going.
Yeah.
And therefore they said, now we've got more fuel for operations.
I think that's correct. There were fewer mid-course maneuvers than was expected.
Yeah.
So that's part of the story.
So who are the main, say, operators of the system and what's the protocol?
So it's actually controlled by the Space Telescope Science Institute, which was created for the Hubble Space Telescope, and most of the space telescopes that go up are controlled through the STSCI. There are international teams that decide what each instrument will look at. So the commands, I think the commands all go up from the Deep Space Network, even though they're created in the Space Telescope Science Institute. But it's a collaboration between the European Space Agency, NASA, and the Canadian Space Agency. And there might be a JAXA instrument on. I don't remember whether there is or not.
So did they begin like with a fixed schedule of what they wanted to investigate and modify that?
They undoubtedly began with a fixed schedule of what they wanted to observe, but that also undoubtedly changed because they launched about 20 years behind schedule, and it's easy to change your mind in 20 years. And the problem was a lot bigger than they thought it would be, which is why it took so much more money and so much more time to do. I don't think they understood how difficult it was to cool the spacecraft. Nothing had to be passively that cold before. So except for the cryo cooler on Miri, it's all passive cooling. And the Miri cooler is a closed loop like a refrigerator, not like the other instruments which used up like a liquid helium cryogen or something. You only had so much time, you ran out of cooler and you're done. With the JWST, that system will run forever. So it's only the maneuvering fuel. It's a limited factor. Yeah.
You know, I was wondering, we know if one of the things that James Webb is going to be able to do is to maybe resolve the the precise number for the Hubble constant.
That is undoubtedly on people's minds. It will, by looking at the redshift, by precision redshift measurements, be able to provide a precise number for the Hubble constant. But under these circumstances, you really have to worry a lot about the difference between precision and accuracy, because different methods give you different values for the Hubble constant. Just because you made one that's very precise does not mean it's right. It could be precisely wrong instead of sloppily wrong. You just don't know until you figure out what are the systematic differences between the different methods that give you different results to begin with. Yeah.
In the early years of the Hubble Space Telescope, they had a program where students and ordinary people could submit projects. Do they have anything like that for?
There's nothing like that at this time for JWST that I know of, because it's so overwhelmed with objectives. When the Hubble Space Telescope went up, its primary function was the Hubble Key project, which was to use Cepheid variables to derive a value for the Hubble constant and the expansion of the universe. And basically everything else was great. And so they had room to stick in some other programs. Now, of course, nobody knows what the Hubble constant is anymore because the different methods give you different results. But JWST has a lot of science objectives that are considered high priority, especially seeing the first stars and galaxies. So unsurprisingly, they have too many demands for their science to let people do that yet. So at some point they may do that. I don't know. Nobody from the JWST asks for my opinion on anything. And if they got it, they probably wouldn't pay attention to it. So, yeah.
So maybe a little bit off topic, but can you speak to the issue of using, I think it's type 2 supernovas as standard candles and kind of working through the whole constant that way?
Yeah, it's type 1 supernovas.
Okay.
Yeah. So they all explode at roughly the same time when the central white dwarf has achieved the Chandrasekhar limit, becomes unstable and disassociates itself and leaves behind either a black hole or a neutron star. That point is slightly variable because you can exceed the Chandrasekhar mass if you have a rapidly rotating white dwarf that will support a higher mass. But the thing that bothered them the most, that actually made it possible to do that, was special relativistic time dilation changes the shape of the curve as a function of redshift. And once they figured that out and how to get the curves normalized by time dilation versus redshift, then they all look the same. They all have this. So you do a whole bunch of supernova and you compare their light curves, they all look the same. And that justifies the assumption, along with the Chandrasekhar mass, that you're looking at something that is a standard candle. Then early on, there was a complaint about maybe dust getting in the way is changing the shapes of the light curves, but that doesn't seem to have panned out or carried much water, as they say. And so it strikes me as a reasonable method. Nobody's found any big flaws with it yet. There's always somebody who's going to complain about it or suggest they have a different theory. And of course, there is a cottage industry of people who have a theory for everything out there. And if you hint that one of their favorite theories might be true, they will be all over you with it. Yeah.
You said that the JWST hadn't detected any so-called population of stars.
Yeah.
Yeah. What's your feeling about that? Do you think it will get there eventually? Do you think they're there to be found?
Well, I think it's pretty obvious that they're there to be found because you've got to start stars off somewhere. So if Big Bang cosmology is a reasonable model for the evolution of the universe, then there have to be population-free stars somewhere, but we don't really know when they're started. So remember that the pre-launch slide gave us 200 to 400 million years after the Bang time window. We're already seeing galaxies down there just over 300 million years. They're small galaxies, but they're galaxies. And they're evidently not population-free stars. They're stars that have already been through at least one, maybe two generations. And so where will you find them? It may be that JWST is still not big enough. Now, John Mather, who's the principal scientist for the mission, said he thought that JWST would see as far as redshift 30. we're seeing redshift 20 is a requirement. Redshift 30 is what he thinks you can see. The highest spectroscopically confirmed redshift we see is 13. And that photometric redshift of 16 didn't pan out. And so it may be that you need longer exposures staring at the right spot. My guess is if you're going to see population 3 stars, it will only be by looking through a gravitational lens. I don't think you'll ever see them if you don't do that. And there aren't that many gravitational lenses around. You gotta look for them. And I think that's the way. It may be that they will need a bigger mirror. Now, before JWST launched, but after it was supposed to launch, there was a plan. NASA started not planning for what they call the high definition space telescope, which would have a 12-meter segment. But I think mostly optical and not infrared. You're going to go back to the Hubble Space Telescope. But after JWST cost $10 billion for a 6.5 meter mirror, people sitting around the desk looking at 12 meters decided we'll wait for a while because it's going to cost a lot of money. And I don't know when, or if, for the time being, that plan is just in somebody's waste basket somewhere. I have no idea when they will do that. But it may be that you'll need a bigger mirror. We'll see.
I read someplace about that some of the earliest stars may have been huge by today's standards. And I'm sure then they wouldn't have lived very long before they exploded. So pretty early in the universe would have been getting polluted with heavier elements. So does that make it really difficult to find the first stars, even if they're there?
Well, that could, but I think what really makes it difficult is you don't know when they started up, so you don't know how deep in redshift you have to go. Remember that the highest redshifts we're seeing, about 13, puts us in the 300 million years after the Bang range, right? The cosmic microwave background, which is right on top of the Bang, 300,000 years, has a redshift of about 1100. So that small space in time spans an enormous range of redshifts. So if you extend your observing wavelengths out to see redshift 20 or 30, well, maybe you need to see redshift 100 to see those stars, because if it's 1100 for the cosmic microwave background, who knows where it is in there. So it may be that we just don't have the wavelength or brightness capability to see them yet. Jeff?
As far as using a gravitational lens to image a star or a very early galaxy, is there an optimum distance from the object to the lens to us? The lens usually at about the 50% point. And as we go further back in redshift, are we going to need to find gravitational lenses that are closer to the optimum point for that distance? And are there telescopes that are looking for candidate gravitational lenses for those greater distances?
I don't know if there's an optimal distance. Gravitational lenses work like, but not exactly the same as optical lenses. So I don't know if there's an optimum position. My guess is you will want to look for more distant gravitational lenses if you want to see more distant objects behind them, if only because the further away the object is, the dimmer it is. So if you have a nearby gravitational lens that can give you 1,000 power magnification, that might still not be enough if your object is so far away, it's just too damn dim. But if you get your lens farther out, magnified by a factor of 1,000 or 2,000, now you've got some throw towards you so that you can spot something. And so my guess is, yeah, you'll need to see farther away the lenses. But whether there's anybody looking for those lenses, I don't know. That it?
I wanted to ask you about, so I'm inferring the point of your surface slide.
Yeah. Yeah.
Or direction orientation. So What, can you speak to like the instrumentation? What kind of degradation in that time is protected if any, from the service? Just,
Yeah,
and, you spoke earlier on the.
yeah.
So,
We could send a bunch of guys out there to Washington.
So, speak to that as far as like.
Yeah.
Mechanical.
Sure, I think the biggest problem for degradation is cosmic ray hits on the detector. Because they permanently knock out pixels.
High energy.
Yeah, and so I don't think there'll be much into a mechanical degradation. The micrometeoroids aren't going to be a big thing on the mirrors. If you hit something really big, then of course, but that's never happened.
The secondary.
Yeah, so I think the biggest problem will be cosmic rays affecting the detector. On the micro shutter array, they've already several fake open, so they know once they can't control, they see that, and they test it occasionally. So that might be another point of failure for the near infrared spectrograph is when those little nano windows just stop working at some point. But there's 248,000 of them, so you've got plenty of them. But it's the detectors that are sensitive to cosmic rays that's really going to be the biggest problem. But I think 20 years, it's just not long enough to be a significant player. So your real problem is going to be the field. You'll still be able to do just about everything now then that you do now after 20 years.